Now, and it seems you did.
We are live.
Good. So welcome to the penultimate session of PEPM this year. And we have two talks. The first is by a bunch of people from Aalborg University, and it will be presented by Hans Hüttel, and it's about the type-safe structure editor calculus. So please go ahead.
Thank you, Torben. This is work that was done by 4 of my former students and myself during the first lockdown last spring. And it's work on a type-safe structure editor calculus. As it happens, we tend to think of programs as text that we edit with a text editor and then turned into an abstract syntax tree using a parser, but one could use a syntax-directed editor for that. It's an old idea. It goes back all the way to the Cornell program synthesizer from 1978, and the Cornell program synthesizer is actually an editor that lets you build an abstract syntax tree directly by using a cursor that you can move the cursor up and down from side to side and put in new branches of an abstract syntax tree, and you can never build anything that's syntactically incorrect. But you can still create programs that are not well typed, and you could also stop at some point and say, I don't know what to do now, and then you'd have an incomplete AST until you finish your AST. Now, Sir Omar and others introduced a hazelnut calculus. The hazelnut editor calculus lets you describe exactly that. You can describe using hazelnut programs with holes, meaning incomplete abstract syntax trees. And hazelnut has a dynamic semantics and a type system, a bidirectional type system that will let you execute partial programs and type partial programs. And any parts of the program that are meaningful can still be evaluated. And in this talk, we're going to describe work on a related node. We're going to describe a calculus of edit action that lets us describe edit sequences on functional programs. And we're going to describe a type system that's very different in spirit from that of hazelnut. It's a behavioral type system, and it guarantees that well-typed edit actions, if you've got an edit action, a composite edit action, then the program that you'll build, the incomplete, possibly incomplete program that you build, will also be well typed. Now, when we edit a program, we've got a cursor. Think of the Cornell program synthesizer. There's a cursor that points to a subtree that we're manipulating or extending, and we've got holes, 0 more holes to be filled out. Sometimes the cursor is at the hole, sometimes it may not be at the hole, it may be somewhere else if we want to delete something, say. Here's an incomplete program in our favorite functional programming language, the lambda calculus, lambda A, lambda B, lambda C. You've got the cursor at the sub-expression B plus C. The hole is elsewhere, it's at the second argument. We could also place a breakpoint if we want to say that we want to evaluate the program as far as the breakpoint. There's no breakpoint in this one, but we'll get around to that. So these are the terms that we can edit and build. In our editor setup, we manipulate functional programs, meaning abstract syntax trees from an applied lambda calculus. And we've got cursors, we've got breakpoints, we've got holes. The programming language is an applied lambda calculus. Abstract syntax trees are given by these formation rules. What you see here is completely standard. Variables, constants, application abstraction. We can place an expression in a cursor. We can put a breakpoint around an expression, and we can also add a hole, and this is how we can get incomplete programs. Now, here's an example of an AST with a hole. This is in fact the term we just saw. Lambda A, lambda B, lambda C, A plus B plus C, and the cursor is enclosing B plus C, and we've got 3 arguments now, 1 and hole and 7. Here's the hole and here's the cursor. Now, suppose we want to move the cursor up. Let's see what we did. We moved the cursor up. Now it points to A plus B plus C. It's enclosing A plus B plus C. The cursor is moved now. We could then move the cursor takes a few steps. I'll jump to the place where the cursor is now at the hole. Cursor is now surrounding the hole. We could then add a new expression at the hole. We did that. We added the numeral 2, and the cursor is around the numeral 2. And now we could evaluate this term. But let's say we only want to evaluate part of this expression. We move the cursor, insert a breakpoint, then move the cursor back somewhere else. The breakpoint is now around the sub-expression C. If we evaluate that, what do we get? We get 3 plus 7. The breakpoint's around the 7. And that's precisely what we can do in this editor calculus. We can describe incomplete programs. We have breakpoints. We can evaluate as far as breakpoint. We can add holes. We can replace holes by expressions, and everything's well typed. In our editor calculus, we have conditional expressions, and something else that is interesting about our editor calculus is that we have conditions that describe the structure of an AST, and what we have is in fact a spatial logic. The formulae in our spatial logic is given by, well, a formula phi. What can that be? It could be a Boolean formula using negation, conjunction, or disjunction. And then we've got the modalities at D, diamond D, and box D, where D are atomic propositions that tell us what's actually at this current node. So informally, at D means that the cursor points to a node at which D holds. So if we write, say, at var X, that means that we're currently the cursor is currently at a node in our AST where there's a variable. Const C means this is a constant. App means this is an application. Lambda, well, lambda extraction, or we can also say that we have a break or hole. The modalities, diamond and box, tells us that some node further down in our tree satisfied D, and box is the next time modality saying that every node in an immediate subtree satisfies D. Anyway, so we've got conditions as well in our editor calculus. Sorry. Here's the editor calculus. We have prefixes as in a process calculus. Prefixes can be an eval saying we want to evaluate the syntax tree. We've got substitutions that let us introduce variables, abstractions, applications. We can move up and down. We can navigate with the cursor. Child n says go to the nth child, or parent says move up one level to a parent node. The editor expressions, capital E, are prefix expressions using the prefixes I just described. They're conditional expressions, biconditionals, in fact, sorry. Phi arrow E1, E2 means if phi holds, then evaluate E1, or if phi is not true, then continue as E2. We've got sequential composition, denoted in this slightly funny way. Recursion, we've got recursive expressions as well, because they turn out to be handy if we want to repeat behavior, if we want to repeat edit behavior. Because we have recursion, we need to have recursion variables. The nil or 0 is a very boring edit expression that does nothing, but sometimes we want that. Anyway, so that's the editor calculus. The semantics of the editor calculus is a small step operational semantics. Transitions in our semantics are of the form: given an edit expression E and an abstract syntax tree A, then we can evolve to E prime, and the abstract syntax tree becomes A prime. It turns out to be useful to be able to record the edit actions, so that's what we do with the alphas. The labels alpha denote edit actions. Anyway, I'm not going to present the full semantics, just some highlights, just to show you what conditionals are like. If the abstract syntax tree satisfies the condition phi, that's a satisfiability relation, I'm not going to define that here, then we continue as E1 and no edit action happens. If we want to evaluate our abstract syntax tree, eval dot E, then if the abstract syntax tree A, that's the second component of configuration, evaluates to the value V, then we record the edit action V and we become E and A. Sequential composition, as you would expect there are two rules for that. Here's one of them, the one that says that E1 can proceed a little bit and become E1 prime, then E1 followed by E2 becomes E1 prime followed by E2. And the abstract syntax tree updates accordingly. Anyway, but that's not all, because if you recall the syntax of the editor calculus, we also had the child and parent and substitution prefixes that let us introduce variables and abstractions and move to a child, move to a parent. And we must have rules for that as well. There's a rule that says that if we have the cursor at A1, A2, then executing a child, oh, that sounds horrible. Executing the child1 prefix lets us move the cursor inwards. If we execute a parent, then we move the cursor outwards. Finally, substitutions, as I mentioned before. Let us introduce variables, or rather replace what's inside the cursor by the syntactic entity that corresponds to the substitution. Var lets us introduce a variable. Lambda x lets us introduce a lambda abstraction. So these are some of the highlights of the small step semantics. Note that these rules were for configurations. There is a rule that connects these rules that only deal with abstract syntax trees to the syntax, to the semantics that deals with configurations. I will not present those here. Anyway, so that's an editor calculus. We've got an operational semantics for that, and now the natural question to ask is when can edits go wrong? We're at to define a type system that lets us prevent edit actions from going wrong. Here's an example of something that could go wrong. Here's an expression, or rather here's a configuration. The red part is our abstract syntax tree. The black part to the left of that is an edit action or edit expression. This is a conditional expression, or rather it's a sequential composition, and the left part of the sequential composition is a conditional expression. It says that if it's not the case that further down there are a lambda abstraction, then we move to child 1, leftmost child. And once we've done that, we insert a variable. We replace what's underneath the cursor by a variable, and then we evaluate. This looks fine, but it's not fine, because if you look at this abstract syntax tree that we got, every path encapsulated by the cursor contains an abstraction. So this means that the conditional expression does not hold. The command is never executed. It means that the first part of the sequential composition terminates immediately. We insert a variable, and there's a runtime error because now we try to apply a variable to the constant C. There's a runtime error. We don't want that. What do? We'll build a type system such that will have a nice property that well-typed programs, or sorry, well-typed configurations cannot go wrong. So how do we set up such a safe type system? Well, in the following, we assume that the programming language is also typed, and we consider a simpler type lambda calculus, where type judgments are of the form given some type context, gamma A, then A has type tau. And it's the usual simply typed lambda calculus with with the function types. Anyway, so we also need to have a type system for editor expressions, and once we got that, we can type configurations consisting of abstract syntax trees and editor expressions. Judgments for editor expressions are relative to a type context that lets us type variables, and there's a path that tells us what position we're at, or sorry, what position the cursor is at. And all we say that an editor expression is okay. A path is a path. It's a path from a root to a specific node, and it indicates if we're going through child 1 or child 2 as we pass down the tree. So the types are sequences of 1s and 2s. And an editor type context stores for every path. In fact, it tells us for every path the type of the sub-expression at the end of the path and the type context that we need to find that type. Okay. Some highlights from the type system. Here are 4 interesting type rules. One is that if we evaluate, or rather if we have an eval prefix, then that's okay if the continuation E is okay. If we have, that's rule TCH1, if we have a child prefix, navigate to child number 1, then the continuation, capital E, is well typed if we can extend the path P with a 1, and we become well typed, and we require that what we see at the continuation of the path of P1 is gamma A. And we have a similar type rule, but if we move up, again, the continuation must be well typed, and we have a condition on the path. Sequential composition is not surprising either, but here's something. This is the part of the type system that shows us that this is a behavioral type system. This type rule is inspired by linear logic. Here we split the path in 2. We have some part P prime that deals with E1, and some other part of the path P prime complement that lets us deal with E2. I don't have time to give the full details. It's a bit technical. Have a look in the proceedings for the full details. But this is the crux of this. We split the resource information in the path in 2 to type the sequential components. Anyway, our editor calculus is type safe. A well-typed editor expression stays well-typed. If we have a well-typed configuration, what do I mean by that? I mean that the editor expression E is well-typed and the abstract syntax tree is well-typed, and this configuration can reduce, then we are also well-typed after the reduction. And this P, gamma E down arrow alpha denotes that we've updated the path and the type context with respect to the edit action that we performed. So if, for instance, the edit action was one that took us 1 level further down the tree, P is extended. So well-typed editor configurations can't go wrong. Or rather, they satisfy subject reduction. Now I'm going to tell you that well-typed editor configurations can't go wrong, sorry. In order to define what it means to go wrong, we have the usual notion of an error predicate. An error predicate tells us which configurations are in error, and the configuration is an error configuration if either the edit action or the abstract syntax tree leads to an error. Again, I refer to the paper for the precise definition. It's quite lengthy. This theorem tells us that if we are well typed according to the type system, then our type system is not an error configuration. And because we have subject reduction on the previous slide, these 2 taken together give us the usual safety property that once well typed, we're always well typed. Now, the results of this work are that we've introduced an editor calculus. It's type safe. If our programming language is the simple type lambda calculus, and if our editor expressions are well typed and the abstract syntax tree that we start out with is well typed, then we will always get a well typed, possibly incomplete program as a result of our well typed edit action. We cannot build an ill-typed program from a well typed incomplete program. One thing that I haven't covered here, and that's not covered in our paper, is that in fact this editor calculus is Turing complete. So we can write some fairly complex edit actions in this tiny calculus. And this is interesting in itself. And it all involves, proving this involves representing the natural numbers using abstract syntax trees. but I will not tell you about that. Anyway, there's lots more work to be done. What we considered was the simply typed lambda calculus, and we considered an editor calculus in which edit actions could not be undone or redone. Obvious next steps, if we want a realistic editor, is to expand the editor calculus with undo and redo commands. Of course, that will complicate the semantics quite a bit, but that would be a nice next step. Another direction for further work would be to think of here's a program that I want to build, or here's a program that I'm unhappy with and I want to modify it so that it becomes something I'm happy with. What does edit distance mean? This is something that's well known from say the Levenstein distance. What would that look like in this setting? Finally, if we look at our type system, we require explicit type annotations. If we ever want to implement this in a setting where there's type inference involved, it would be nice to have a notion of type inference to make annotations unnecessary. That would be also a very nice next step. Anyway, so I think that's more or less it. That was definitely the last slide. Yes.
Any questions? Well, I have one then. So you showed us these modalities, the master space, box, and diamond for some properties of the current node.
Yeah,
and nodes below
maybe
it.
I should share the screen again, Torben.
Sure, yeah, probably a good idea.
Let me see how I have to. Yeah, okay, sorry, I should do that. Here we go. I think. Where's it now?
We can't see anything.
No, I know you can't see it. It's because I'm trying to get this to work okay, but oh yeah, here we go. Wait a second. Sorry, I'll do this again. Here we are. Yes.
Okay. Yes.
Sorry about that. So and you. Oh. It's not fair. Sorry about it. But Torben asked that question, and while you're asking that question, let me fix this thing.
Okay. Yeah. So you had these modalities for things in the current node and children nodes. Have you considered maybe adding a modality for going up in the tree, so you can talk about parent nodes and?
Oh, you mean some kind of pass modality?
Yeah, that you can go up and then down again, maybe, if that would be useful.
Yeah. Okay. So maybe can you actually see this?
Yeah, you can see your whole desktop actually.
Wow, that's not so interesting, is it? I'll better stop sharing that because there's lots of crap on my desktop. Anyway, okay, so Torben, the question you're asking is, would it be nice to have a backwards modality, so to speak, that would let you say further up the tree something holds? Yes, that would be interesting. I wonder if you were say to say if I am part of an application, then go upstairs and delete me.
Something like that. Yes.
Yes. Yes. Yes. Then you could do that. I think it would be. Oh, yeah. Now I wonder what the type rule would look like if you wanted to do that. Then you'd have to find a prefix of the. You have to check that your path allowed that.
Yeah.
Yeah. Because the type judgments are relative to a path, you have to. Yeah.
Yeah, and also your modalities only talked about either the current node or all the nodes directly below, or some node.
Yes.
You want a specific child.
Yes, my grandchild, for instance.
Yeah.
Yes.
or just the first subchild and not
Yes.
necessarily the second?
Yes. So that would be interesting too. Of course, that would. Yeah. But those are interesting because I mean, then you'd have a full spatial logic. I don't think decidability would not go out of the window because all trees are finite. But there's something to think about there. Nevertheless,
Yeah.
I think there are some results by Radu Mateescu and his friends on the time complexity of model checking. That's because now we're looking at model checking for spatial logic like that.
Yeah. Okay. So, any other questions?
I have a question.
Yeah.
So, what about applications? Have you thought about, for instance, exposing this in an IDE?
Yes, well, the cheeky reply to that, we've got an application in lambda calculus. No, but the less cheeky is that yes, in fact, the reason that we're doing all this work is that some of us, me in particular, we're involved with a local startup company they're building a structure-oriented editor for a functional programming language. So yes, this is being implemented.
What's the just out of interest? What's the business model there? I'm not sure. Structural programming.
We should take that the business model. We should take that offline.
Yeah, we probably. But okay, maybe I should ask. Can I ask a more relevant question? I mean, what's to be gained by having a structure editor in this situation?
Well, actually, the reason for having a structure editor is that it gets even hairier now. Is that we're interested in building. We have, in fact, a visual functional programming language, and if one is a beginning programmer, then maybe structure-oriented editors are the way ahead, because you're not so keen on syntax errors, and that's why one does syntax to direct editor.
So following up on that would you actually envisage exposing the entire calculus to users in the IDE, or is this just something for IDE developers?
One would have, let's just say, one would have a visual version of the editor calculus. I mean, navigation is all you want.
Yeah. Okay.
And
so
and pointing and clicking. So now we're at this. Now we're at the sub expression. Now evaluate this. Evaluate until this sub-expression is reached.
I mean, it may not necessarily expose the entire expressive power of the calculus. You just the bits that
maybe not. No, maybe not. No.
Okay. Well, I'd be very interested to see how that pans out in practice. It'd be cool if it gets used in anger.
Yeah. It would.
Yeah. Any further questions? It seems not, so let's move on to the next talk, which is by a bunch of people from Oregon, and I believe it's Zachary Sullivan who will be talking about strictly capturing non-strict closures. So please go ahead.
Hey, I'm Zach. I apologize if there's noise. They just started doing landscaping outside. But I'm presenting strictly capturing non-strict closures, and this is joint work with Paul Downen and Zena Ariola. This paper is all about running higher order functions and implementing them in our compilers. So, for example, we may have this program here, which has a higher order program in this inner let. Lambda zy, which is returned to an outer scope and then applied to 3. And if we were to draw the activation records for an execution trace of this program, we would have to create this pair of an activation record and the code for lambda zy. This point, can you hear me? I'm sorry. Okay. We have this inner pointer, which will point to the environment in which that function occurs. We call pairs of environment and code closures. And here they are a feature of the runtime system. Our runtime system knows to create closures when we encounter functions. In compilation, we have a problem of what if our target language does not automatically create closures? For instance, when compiling to C, we don't have this ability to capture closures. And the solution is to make closures explicit by generating code. This process of making closures explicit in the language is called closure conversion. And it transforms a language with open functions, that is, ones containing free variables, into functions that are completely closed. And it's used in Schemes Rabbit and Orbit compilers, as well as SML New Jersey. You'll notice that these are call by value compilers. So a question becomes, what about Haskell? In fact, Haskell does do this at the end of their compilation phase at code generation before making something similar to C. But we haven't studied closure conversion in non-strict languages in general. The contributions of this paper are to explore non-strict closure conversions, that is, call by name and call by need. Therein, strictness is an essential aspect for closure conversion to be useful. Additionally, we propose a partial closure conversion that allows us to capture closures in Haskell's intermediate language, which is lazy. So as background, I'll first examine closures in strict languages. Returning to our example program, I would like to show how we describe this evaluation in our paper, which is using a big step semantics. We capture a closure with the following rule. We have a configuration, sigma, which is a local environment, and a function, lambda x m. And to return a value for that, we need to pair the current environment with the code. And in our example, the only thing in the environment is y bound to 3. And so we turn a closure with just y bound to 3. When we want to enter the closure, this function closure, it's done at the application site. And we evaluate the left-hand side of an application to get a closure. And our semantics will pattern match on that closure and instantiate a new environment here with just the formal parameter. It takes the environment out of the closure and adds a formal parameter before evaluating the body. And in our example, we have the closure of the code lambda z y and y bound to 3. And then when we enter the closure, we have the old environment from the closure and the formal parameter. Now, how do we closure convert this example? We, instead of returning just a function in the inner let expression, we create a data structure which has a pair of a representation of the free variables, in this case just y, and a new closed function, which also takes a pair, the first part of the pair being a pattern match on the data structure, and the second part being the normal formal parameter. And we generate code to enter one of these objects by unpacking them, pattern matching on the environment part and the function part, and applying the close function to the environment paired with the formal parameter. So how can we run this closure converted program? Well, functions no longer need to capture free variables. So we have a new lambda rule where we just return a lambda. In C, this could just be a function pointer. And applications don't need to unpack them. So we'll evaluate the left-hand side of an application, get a function like a function pointer, and we'll enter the body of the function with only the formal parameter in scope. So what did we do with strict closure conversion is we made it so that we no longer need to consider closures in our runtime. Our runtime is closure ignorant. And C has this property, so it's a valuable conversion if we're going to compile to C, which is very common. How does this transfer to non-strict languages? Well, non-strict languages are going to require more closures than strict languages. Take this new example program where we have a few bindings, and in non-strict languages, we're not going to evaluate those until they are, until the variable occurs. So if we were to draw activation records here, we would need to create a closure for the unevaluated expression x plus 2 to keep track of that free variable x. I call these closures thump closures, and they are needed in non-strict languages in addition to function closures. Specifically in call by name, how do we capture and enter these closures? We capture these closures in a let rule where we put a closure in the environment for the bound variable before continuing the body of the let. And in our example here, the only thing in the environment is this first x. When we enter a closure here at y, we look up a variable in the environment. It will always be bound to a closure. And then we instantiate the environment inside of that closure and evaluate the unevaluated expression therein. So in our example program, we had a closure with x in it, and we instantiate that environment with just x, and then evaluate x plus 2 when we're looking up y. Now, how do we closure convert this code? Well, we use the same trick we did in strict closure conversion for function closures, and that we, instead of just having an expression on the right-hand side of a binding, we return a data structure with the free variables and a closed function that pattern matches on the free variables. And unpacking this is exactly the same too, where we'll pattern match on one of these packages, and we'll apply the function part to the environment part. So how can we run this call by name closure converted program? The natural thing to do would be to evaluate it in a call by name target language, which includes non-strict data types. And as a reminder, non-strict data types are not evaluated until forced by their context. What does this mean exactly? Take, for instance, existential data types, which occur in our translation. If we have a pack expression and we want to return a call by name value for that, we won't evaluate underneath the constructor there. M could contain free variables, so we need to return a closure to capture the value of those free variables. And when we unpack this, we'll also pattern match on this closure and put a new closure in the environment before continuing with the body of the unpack, which is in. So in closure converting our program into a call by name target language and using non-strict data types, we haven't removed the need for closures in our runtime, which was one of the goals of closure conversion. And non-strict functions nor let expressions also require closures in our runtime. So what if we simply remove the closure constructing aspect of non-strict data? Like this. So instead of capturing the closure for pack, we just return pack. And instead of unpacking a closure and creating a new one, we just put L in the environment as X. Well, in our example program, what's going to be stored in the environment for Y? It'll be this code, pack X, comma X, and then the body. But if you notice, we're going to put another X in the environment right after. So when we end up entering the closure for Y and then looking up the variable X, we're going to access the most recent X that was put in the environment, which means we have a dynamically scoped program now. So using non-strict data after closure converting, but not using the closure constructing version of non-strict data will be incorrect. It won't preserve the semantics of our source language. Why didn't we have this problem for call by value closure conversion? Well, call by value data types do not require closures. This is the call by value version of evaluating pack to a value. We evaluate under the constructor, which means we would look up all the free variables that were in our closure converted package. And we don't have any closures in unpack either. So fortunately, closure converting for call by name also did a thunking transformation. All of the expressions that were turned into packages were hidden underneath lambdas. So in that way, we've intuitively preserved the semantics of our call by name language when we closure convert and then evaluate it in a call by value target language. And we prove this in the paper with a family of logical relations. So returning to the question of how do we run our call by name closure converted program, we have this table here. So our source language, call by name, was, I used the phrase closure ignorant to mean we don't need closures in our runtime. We do need closures in our call by name runtime. And closure conversion in that case is correct, but it's not useful for compilation where we're trying to reduce the need or eliminate the need of having closures in our runtime. The call by name prime language, in which I described just forgetting about the closures of non-strict data, doesn't use closures, but it's not correct. And because we thunked when we were doing call by name closure conversion inadvertently, the transformation is correct in a call by value language, like our call by value strict language in the background section. But of course, that will construct closures for functions, so it's not useful for compilation. The language that has it all is this call by value prime language that doesn't create closures and is correct. So we consider that the useful one. If we're going to do closure conversion on a call by name language, the target language ought to be strict if we're actually going to capture closures. In addition to preserving correctness, our call by name closure conversion preserves types as well. So strict closure conversion preserve types by hiding the environment and existential data types. So for example, if we have these two functions that have type int to int, but different free variables, the second one has the free variable y, then after closure converting, without the existentials, they would have different types. So in strict closure conversion, we provide a type translation that hides the representation of free variables. We do the same in call by name, but we have to modify it slightly. We have a type translation for results that are returned from evaluation. And this looks very similar to that of the strict closure conversion translation. And then we also have a translation for values, which are thunk closures. Every variable will be bound to a thunk closure, which also is an existential package, but the closed function inside of it does not have a formal parameter. How does this extend to call by need languages? Well, what's additional in call by need languages is sharing. So take this example where we don't want to evaluate 2 + 1 twice. Say we use our call by name closure conversion on this, we'll create a package for 2 + 1 and unpack it twice. And as we mentioned in the last section, the important language to evaluate this in is a call by value target language that doesn't create closures. In that language, this expression will be evaluated twice. So we've lost sharing and haven't preserved the semantics of call by need. The solution is in our target language. We need to replace thunk closures with the result of evaluating them after we do it the first time. And we do this by extending our target language with mutable variables and sum types. And this is similar to how you might implement delay and force in a call by value language. So the call by need closure conversion becomes this, where we have this special store macro, which will place the package in the heap, and then a memo macro, which will intelligently look up that heap object. And well, here's the code for those. It will intelligently look up that heap object, and if it was tagged with NL, it will return the value because it was already evaluated to a value. And if it was tagged with NWrite, then we have an unevaluated thunk, and we need to evaluate that thunk and then update the heap value. Just like the call by name closure conversion, this preserves types. The result translation is unchanged. All we need to change are values, which are now placed in the heap with this ref type, and they're also a sum type. So we tag in left if it was already evaluated, and in right if it's a thunk. As I said before, for call by name closure conversion, we proved that correct with a family of logical relations. And in call by name, for example, we had a relation for values in the source and target. A source thunk would be related to a target package if their configurations were related. Extending this to call by need, we have values that are in a heap and they depend on the rest of the heap. So we extend this relation with a pair of a source and target heap. And if you notice, a thunk in the source language is related to a tagged thunk in the target language if their configurations are related. Now, because we'll update things in the heap, we also have another relationship where we may have updated something in the source heap, we evaluated a thunk and got a function closure out. And in that case, it'll be related to a tagged value in the target language. Is this sufficient for proving call by need correct? No, because we need to reason about updating. The first time we evaluate X, it is a thunk, but the second time we evaluate X it's a value. So we need to reason about when we put something in the heap, we need to know that it's true now and after it is updated. And so for correctness, we conjecture that there is a relationship on future heaps, such that if something is a value now, then it will be a value in a future heap, where a future heap we could have replaced any thunk with the result of evaluating it. And such a notion of future heaps would apply to a more general notion of memoization with explicit heaps. So now we know how closure conversion is done in non-strict languages, and that the target of these closure conversions is a strict language. It's not hard to see why in Haskell it is done at the code generation phase at the end of compilation, because we're switching to a call by value language. If we want to do this in our intermediate language where we know how to do optimizations, then we need to be able to lift the idea of capturing a closure into our intermediate language. And this is the idea of partial closure conversion, where the notion of closure, which is low level, will be incorporated into our intermediate language, which is lazy. So there's a conflict of evaluation strategy here. How might we do this? Well, let's take this example program where we want to capture a closure for y plus 1. We do this by the same closure conversion, but here we introduce a strict let binding, which will force this package to look up the current value of y. If it was a normal lazy binding, it wouldn't do this. And then we also, for eliminating it, we create a new wrapper function for x, or wrapper expression, which will tell the lazy runtime how to access this closure. The wrapper, which is in red here, is handed off to the lazy runtime, but the blue part here is strict. So we're mixing evaluation strategies. This is the same idea of how strict unbox types are introduced in Haskell's compiler, or Haskell's, I say Haskell's compiler, I mean GHC. This is how they're introduced in GHC. So to get this to work in GHC's core, our intermediate language must include closed functions, strict data, and strict let expressions. The second two are already included in GHC's core language today. So as a summary, we showed that closure conversion is not useful if we use non-strict data types, because we'll still need closures in our runtime system, or if we remove those, they'll be incorrect. We also briefly discussed why correctness for call by need closure conversion will depend on a notion of valid future heaps, which we conjectured exists, but we didn't finish this proof. And we also introduced a notion of partial closure conversion that allows us to capture closures but still be lazy. As future work, we hope to elaborate the heap-based reasoning about memoization and discover this notion of valid future heaps, and explore the practical benefits of partial closure conversion. If I could leave you guys with one thought, it would be that non-strict closures are strict. Thank you.
Thank you. So any questions from the audience? So it doesn't appear that way. So let me ask a possibly naive question. So basically what you have described in the way you pack and unpack and etc. closure conversion, that's how it's usually done when you implement a lazy language. So is the main contribution that you have formalized this or that you have tried some alternative methods and discarded those as not being useful?
The main contribution is that we formalized this, but we also discovered that it doesn't make sense to closure convert and stay lazy after closure conversion.
Yeah, that's
And
somehow it's not surprising, but yeah, it's nice to have it confirmed formally. So any other questions? We still have several minutes.
I have another question. I'm not sure if this would sort of shed any light on anything at all, but it might be worth considering. Have you thought about kind of trying to unify your approaches by, say, taking call by push value as your starting point? Call by push value being a calculus that quite nicely encodes both call by name and call by value in various ways.
I have thought of that. I'm not sure how. So you can look at the closure conversion as a thunking and then a call by value closure conversion where you have delay and force for call by need, and that the delay and force part, I'm not sure how that relates to call by value or call by push value. I know there's a call by need version of call by push value. So I've thought about this, but I haven't explored it deeply, I guess.
Yeah, any other questions? So another possibly naive question from me is, so you've shown a call by value closure conversion and a call by name and need closure conversion, but lazy languages typically have some applications being strict because strictness analysis has figured out. So can you conversion accommodate having both strict and lazy applications in the same language?
I haven't explored that yet, but if we were to implement a verified lazy compiler, that sort of question would have to be answered.
Yeah, sorry about the clock ringing in the background, but yeah, so any further questions? Otherwise, we can end this session actually more or less on time. So thank you again. And we'll have the last session in about half an hour with another keynote talk by Pat Hanrahan. I'm certainly looking forward to this because it combines partial evaluation and domain-specific languages for an interesting application in hardware. So I'll certainly be here in half an hour. So see you then.
Yeah, the other thing to note is Pat is a Turing Award winner and a 3-time Academy Award winner. So he's an important man.
Yeah, very few people have both Academy Awards and Turing Awards.
Indeed. I'm going to end the stream now.
Yeah, bye.